Now we're going to look at a slightly more involved function in terms of critical points and what type of critical points they are. And there is a similar problem in our book in section 13.8. It's question 26, very similar to this one. So I'm going to work through this example kind of in two stages. First, we have to find the critical points. So we're going to need that first derivative with respect to x and that first derivative with respect to y. And we'll set them both equal to 0 to get started with. So the first partial x derivative, that's right, 4y minus 4x to the third. And then the first derivative with respect to y is 4x minus 4y to the third. And what we're going to do is we're going to sort of keep our work separated here. Set both of these equal to 0 simultaneously. Remember, they both must be equal to 0 simultaneously. 4y cubed equals 0. Now, it turns out that solving these two nonlinear equations as a system can actually be among the most difficult part of this problem. We are only going to deal with simple cases of substitution in this course, but there's whole math courses in upper division world numerical analysis talking about solving systems of nonlinear and techniques that you can't maybe do algebraically, but you can use with combinations of linear algebra technology. So we're not going to go there. But if I start with this one, I can quickly resolve this to y is equal to x to the third power. Add and then divide by 4. And if I substitute that y value into this one, 4x minus 4y cubed equals 0, and I let y become x cubed, now that equation has only one variable in it. 4x minus 4x to the ninth equals 0. There's a chance that the author of this problem cares about you guys a little bit because this is going to factor nicely. If you factor out 4x, you get 1 minus x to the 8th is 0. So either x is 0 or 1 minus x to the 8th is 0, our zero factor property, one of the biggest in all of mathematics for us to this point. X to the 8th equals 1, and we have an even root, and that means when we take the 8th root, we will have two possibilities. There are 1, 2, 3 separate x values that could generate critical points. And we'll link those together with what y equals. So if we know what x equals, then we could find the y value that goes with each one. So you cube the x value, and it turns out the y is 0 in this case. 1 cubed is 1, negative 1 cubed is negative 1. And so our three sets of critical points are not too bad. 0, 0, 1, 1, and negative 1, negative 1. These are our three critical points. Now, we need to do the second half of this problem, which is identify them. And I was writing too far down the screen, so I'll let that be visible to you. Okay, I'm going to swap papers here. I'm going to write this down. So you already have notes from the first part of this. if we were to calculate the second x derivative, it should be negative 12x squared. And the second y derivative should be negative 12y squared. You can go back and double check those. And then if we start with the first x derivative and we take them with respect to y, you will get a constant 4. And remember, what we're going to do is be checking this second derivative test for whether it's greater than or less than or equal to 0. And we have to do it for each of our critical points. So we're going to test at 0, 0 itself first. All right, we'll check this one. So if x is 0 and y is 0, these are both 0. So we get 0 times 0 minus 4 squared. That is less than 0. And if we go to our handy-dandy formula sheet, we will see that if it's less than 0, then we have here a saddle point. A saddle point. So therefore, f of 0, 0 is at a saddle point. Next critical point is 1, 1. If x and y are both 1, we get negative 12 minus 4 squared. That will most certainly be greater than 0. We're not as concerned with the numerical value. And from the handy-dandy list of formulas, the next thing we do is if it's greater than 0, we have to determine what the second derivative is to know whether it's a maximum or minimum. So we get here the second derivative at the point 1, 1 is negative 12, less than 0. And if the second derivative is negative, you have it concave down, quote. That means we have f of 1, 1 is at a local maximum. I want you to try the same thing with negative 1 to confirm that at that set of coordinates, you will also be at a local maximum. It's nearly the same work as the previous critical point. So there we've done it. 3 critical points, and we've determined what type they are. For my students, you should really follow up with, in this section, problem number 18, and I will have the solution to that one written up and posted in Canvas. It has quite an interesting list of critical points. Catch you later.